So we have our definition of dimension. It's the number of vectors in any basis for the space you care about. And the real punchline was from the section immediately preceding this. We know the dimensions of all four fundamental subspaces of a matrix. The dimension of the column space and the dimension of the row space is equal to the rank of the matrix. The dimension of the null space is the nullity of the matrix. And the dimension of the left null space is the nullity of the transpose. There's all sorts of interesting things we can say now. For example, we now have a theorem that connects this idea of geometric multiplicity to the idea of eigenspaces. And the theorem says that the geometric multiplicity of an eigenvalue of a matrix is the same thing as the dimension of the associated eigenspace. And the proof here isn't difficult at all. It just ties together all these concepts. Remember, by definition, the geometric multiplicity of an eigenvalue is the nullity of the associated characteristic matrix. But the nullity of the associated characteristic matrix, we now know, is the dimension of its null space. But its null space is what we define as the eigenspace. So I have a little typo here. This should say dimension of the eigenspace at the end. I'll correct that. So this is just saying, this thing we called geometric multiplicity before is the dimension of the null space of the characteristic matrix, but the null space of the characteristic matrix is the eigenspace. Let's look at an example. Here someone's been kind enough to take this 3x3 matrix and give us the eigenvalues. The eigenvalues are -3 and 5. Well, let's say that I wanted to describe everything in the eigenspace of this matrix where lambda equals -3. Well, how do we do this? We're supposed to look at the null space of the characteristic matrix. -3 times the identity minus the matrix. And how do I look at the null space of a matrix? Well, I typically row reduce that matrix. So I've bothered to find the reduced row echelon form of the characteristic matrix. And here what I'm finding is that there's only going to be one free variable when I study the system that defines the null space of this matrix. And I'll only get one linearly independent solution, and all other solutions will be multiples of this one. So here I'm finding that I have one basis vector, 4, 4, -1, for my eigenspace. This is telling me that the dimension of the eigenspace is 1, and that is the same thing as the geometric multiplicity of the eigenvalue. Let's look at the other eigenvalue. The other eigenvalue is lambda equals 5. How do I describe everything in this eigenspace? Well, the way I describe everything in the eigenspace is by looking at the null space of the characteristic matrix, 5 times the identity minus the matrix. And the way we study this null space is by row reducing that matrix. I plugged this characteristic matrix into the computer, and the computer told me that the reduced row echelon form was this matrix. And from here, I see that I'll have two free variables in my associated system. And this gives me two basis vectors for the eigenspace. And that tells me that the eigenspace has dimension 2, which tells me that the geometric multiplicity equals 2. So again, we see this because the nullity of the characteristic matrix is 2. There are two non-pivot columns as evidenced by the reduced row echelon form.